Hello all. Welcome back for another video lecture for college algebra. Today we're going to cover section 2.2. So what I would like you all to do is start off by taking a few minutes to graph using class calc and then looking up on this page the following 7 functions and relations. So the graphs that we just looked at. So take a few minutes, pause the video to do that, to start out, graph these functions and state the domains and ranges, and then we'll go through them here in a moment. Okay, so now that you've had a chance to look at each one of these graphs with class calc, we can draw them here in our notes and then talk about them. So these are a bunch of different graphs that we're going to see fairly regularly. So when you graphed y equals x squared, you should have gotten what we call a parabola that looks like this. Sorry, a couple of those points I put in the wrong place. So there we go. And so we get a parabola that looks like this. So as we can see, based on what we talked about in the previous section, the domain of this function would be everything, because this arrow goes, the left-hand arrow goes to the left forever, the right-hand arrow goes to the right forever, so the domain here is negative infinity to infinity. So there is no farthest to the left we go or farthest to right. It goes on forever. And the range for this function would be from 0 to infinity, because there is a smallest y value. The lowest this graph goes is right here, and then it goes up forever. The second function here, the square root, looks kind of like half a parabola on its side. So it looks like this. In this case, we can see that there is a farthest to the left option, so the domain would be 0 to infinity. And once again, there is a lowest option, so the range would also be 0 to infinity. So far, those are both functions, hence the name function at the end of their title. However, if we draw out x equals y squared, we end up with a graph that's related to these two, but is not a function because it does not pass the vertical line test. So it ends up being a parabola that is on its side. So it looks something like this. And notice it wouldn't pass the vertical line test. And once again, this has a smallest x value because the farthest it goes to the left is 0. But then it goes to the right forever, so we'd have 0 to infinity for its domain. But the range is anything, because we have an arrow that goes up forever and an arrow that goes down forever. So this would be negative infinity to infinity. Okay. So, now that we've talked about those first few, these are all related to each other, so that's a good thing to remember. But now what we're going to look at is a couple other functions that we've worked with these equations already, or we're going to see them a lot moving on. So, if we move down here, we've got first the cube root function. So this is the same idea as the square function, except we're plugging in, we're cubing things. And because we can cube, when we cube negatives, we still get negative results, we get a graph that looks a little different. Okay, a graph that looks like this. And the domain and range of this, because we get negatives out when we put in negatives, both of these go on forever in both directions. So these would have domains and ranges of negative infinity to infinity. The cube root function is going to look a lot like that, because now instead of cubing x, I'm going to cube root it. And so what I get is I get a similar looking graph, but kind of laying down. So it looks like this. And once again, the domain and range of this are negative infinity to infinity, because it would go on forever to the left and to the right. So those are the cube root functions. So once again, like I said, those are related to each other, and they're related to the squared functions. They have similar ideas. The next one's a semicircle. So a semicircle is simply half the circle that we've looked at previously. So this semicircle looks like this. Okay, and so the graph looks like this. And so we get all the points for the domain. The farthest to the left this goes is -5. So the domain starts at -5. And it goes on to the right to 5. So we get all the x values between -5 and 5. For the range, the lowest the graph goes is -5 down here, right? And then the highest it goes is at these 2 points, which is at 0, y equals 0. So the range is -infinity to 0. And then the last graph here is the absolute value. So we can start at 0, 0, and we go to the right and like this, and we get like a V shape. And so while this graph doesn't look like the squared y equals x squared on the last page necessarily, it does have the same domain and range. It goes on for infinity for domain, any number we want for x, but y has to be 0 or positive. So look at, so those are some pretty common some fairly common graphs that we're going to see throughout the rest of this class. So we've talked about domain and range now, but the other thing we could talk about is whether or not the graph is going up or down in that domain. So that brings us to a few new ideas, which are the idea of increasing, decreasing, or constant. So if the y values are going up for any numbers where a is less than b, so as we go to the right, so these are all for as we go to the right, if the graph is going up, we're going to call that increasing. If it's going down, we're going to call that decreasing. And if it's flat, we're going to call that constant. So I've given us a number of graphs here, and so for each one of these, we can talk about the idea of domain, range, and domain, range, increasing, decreasing, and constant. So let's start with the thing we already talked about, which is domain and range for each one of these first four. So if we look at these graphs, we can do the domain and ranges hopefully fairly quickly based on what we've already done. So I'm just going to list the domains across the top here for each one of these. So and then we'll do range, and then we're going to do increasing, and then we're going to do decreasing, and then last but not least, we're going to put anywhere that it's constant. So we're going to make a little, let's just go ahead and make a little chart here for each one of these. Okay. Let's see how that goes. So for this first one, the domain, we have an arrow on the left, we have an arrow on the right, so that means the domain is -infinity to infinity. Same for the second one, right? Arrow on the left, arrow on the right, so the domain is -infinity to infinity. Third one, the farthest to the left we get is -4, the farthest to the right we get is +4, so the domain is -4 to 4. And the last one here, there's an arrow on the left and an arrow on the right, so that's -infinity to infinity. For range, on the first one, we can see we have an arrow going down and an arrow going up, so that means the range is -infinity to infinity. In the second one, both arrows go down, so that means we're going to have -infinity, but then there is a largest value, which is right up here at this point, which is the y value of 4. So the range is -infinity to 4. In the third one, the smallest y gets is 0, at these 2 points on the x-axis, and the largest y gets is 4 up here. And then for this last one, we have 2 arrows going up, so our range is going to go to infinity, but we do have a lowest value along this line, which if you look closely, each one of these tick marks is 2 units, so that's at -2. So this would go from -2 to infinity. So that we've talked about previously, but now let's talk about this new idea of increasing, decreasing, and constant. So the idea here is as you go from left to right on the graph, is the graph going up, down, or staying the same? So in this first one, if we look, this graph as we go from left to right is always going down. So it's not increasing, but it is decreasing everywhere. So we can say negative infinity to infinity, it's decreasing, and then it is also not constant anywhere. So, and the idea here, remember, is it's as we're kind of traveling across the graph. So starting on the left and going to the right, I'm always going down. So I'm decreasing from negative infinity to infinity. On the second one here, if I travel along the graph, I'm going up first, and then I go down. So this one's going to increase and then decrease. So I increase starting at negative infinity, and I keep increasing until my x value is 0. So I'm going to increase from negative infinity until I get to 0. So I don't tell you where the y value is when I stop increasing. I tell you what x value do I stop increasing at. And then from there, we go down. So this decreases from 0 to infinity. And then once again, this one is not constant anywhere. Similarly, this one is similar to the one before it. I start by going up, but in this case, I start at -4, and I increase once again until I get to an x value of 0. And then from that x value of 0 to +4, I'm going down. And once again, there is no constant. And then the last one here, if I start on the left-hand side of the graph, I'm actually decreasing first. So I decrease from negative infinity until I get to an x value of -2. And then from -2 to 2 on that piece, I'm constant. So I'm constant from -2 to 2. And then finally, from 2 onward to infinity, I'm going up. So I'm increasing. Okay, so why don't you guys go ahead and take a moment, pause the video, and try these 4 at the bottom. Tell me domain, range, increasing, decreasing, and constant. And then when you're done that, you can hit play on the video again, and we will go through the answers. Okay, so now that you all have had a chance to try that problem, let's go ahead and go through the answers for these here at the bottom. So once again, we can do the same thing we just did. We can make ourselves a little chart. So we've got domain, range, increasing, decreasing, and constant. Okay, and so if I make my little chart. Okay, so in this first one, let's start with domains and ranges again. So the domain for this one, I've got an arrow on the left, arrow on the right. So the domain is negative infinity to infinity. Arrow on the left, arrow on the right. So the domain is negative infinity to infinity. Arrow on the left, arrow on the right. So negative infinity to infinity. And the last one, the farthest to the left we go is this point here, which is at x equals -2. And the farthest to the right we go is this point, which is 5. So -2 to 5. Then we can look at the ranges. So for the ranges, I've got 2 arrows going up. So I'm going to go to positive infinity. And the lowest value looks like 0 to me. So I'm going to say the range is 0 to infinity. For the second one, I've got an arrow going up and an arrow going down. So that's negative infinity to infinity. Same thing for the next one. Arrow going up, arrow going down. So that's negative infinity to infinity. And then for this one, the lowest value is actually this point right here at 1, 1. So that's a y value of 1. And the highest value is this point over here at -2, 4. So that's a y value of 4. So the range is 1 to 4. So now we can do increasing, decreasing, or constant. In this first one, we go down first from starting at negative infinity until we get to 0, and then we increase from 0 to infinity, and there is nowhere that we're constant. In this second one, we decrease first from negative infinity to negative 2, and then we increase from negative 2 to negative 2/3, and then we decrease from negative 2/3 to infinity. And once again, in this one, there is nowhere that graph is constant. Then in 55A, this graph, if we go from left to right, is always going up. So it increases from negative infinity to infinity, but it does not decrease or remain constant at any point. And for the last one, we decrease first from negative 2 to 1. Right? This piece goes from x of negative 2 to x of 1. Then we increase from x of 1 to x of 2. And then we remain constant for the rest of the graph, which is from 2 to 5. Okay, so that's the idea with increasing, decreasing, or constant. So now we can talk about some special types of graphs. So on the next page, what we're going to start talking about is this idea of what is called a piecewise function. So a piecewise function is a function where different functions are used to define different parts of the domain. So if we look at this, notice that we have different requirements for different parts of the domain. Okay, so we can actually graph these by hand, but you can actually use your class calc app to use these to graph these as well. So let's go ahead and look at that. So if I wanted to graph this first one with my class calc app, okay, so what I have to do is I have to define different functions with different requirements. So if I put in the first function here, so the first function was y equals the square root of x. Okay, and so there's the normal square root of x function. But I only really want it to be defined from x is greater than or equal to 1. So I can make class calc do that. So you do that by clicking and holding on the green circle there, or whatever color circle it is on yours, and you want to set the domain. So for the domain here, I want x to be greater than or equal to 1. So I want that to be 1 is less than or equal to x. And what you should notice is that if I take that away again, it's removing this little segment of the graph that is less than 1. And then we can come in on our next function and graph the other piece. So the other piece of this graph was negative 3. So we want to graph y equals negative 3. Okay, and we want to graph that for x less than 1. So I come in and I click set the domain again. And this time I want x to be less than 1. And so what we get is we get a graph that has two different pieces. It has this square root piece on the upper right, and it has this constant piece on the lower left. So in our notes, what that would look like is it would look like this. At 1, 1, I've got that point, and then it goes to the right as a square root function. So that looks like this. And then to the left of that, I get this line at negative 3. Now, the thing you have to notice here is that on the upper one, we have or equal to. So this point at 1 gets included. But on the bottom part, we don't have an or equal to. So that point is not included. So what I do is I put an open circle to say that point is not included. Okay. Now, we can talk about domain, range, increasing, decreasing, and constant with these as well, but things could get a little weird. So for domain, it's fairly straightforward. I get all the numbers, right? I have an arrow to the left, arrow to the right, and I don't miss anything in the middle. So the domain is negative infinity to infinity. However, with the one for the range, what we get is we get the value negative 3, so I put that in braces. But then we don't get anything from negative 3 up to we start at 1. And then we go from 1, and this arrow goes up forever. So we get an arrow 1 to infinity. We can also see that this graph is constant on this piece on the left. So that means it's constant from negative infinity until we get to this circle, which is at 1. However, because it's a circle, it is not included. So we put a parenthesis. And then from there, from 1, it increases because this piece is increasing. But because that point is included, because it's filled in, we increase from bracket 1 to infinity. Okay, so that's the idea there. So we could try doing another one of these with our class calc app. So if I go in here, back to my app, and I graph the next one. So I'm just going to change these. So y equals the square root of x is going to become y equals x minus 2. And then I want to change this region to be from 2 and bigger. Oh, whoops, I forgot the x. Let me fix that. Okay, so x minus 2, so I get that piece. Okay, and then I can graph, this graph is now going to be 4 minus x squared, whoops, which I didn't type in very well, 4 minus x squared. And it's going to also have a restriction on it, so I'm going to set the domain again. This one's going to go from from negative 2 to 2. So we get a graph that looks like that. Okay, so I could transfer that into my notes. So we've got this little parabola. Notice that the endpoints are not included, so I'm going to do open circles. And I get a little parabola that looks like that. And then I get this line portion, but notice the line meets there, so that actually gets filled in. And so we get a graph that looks like that. So in this case, the domain starts at negative 2, but negative 2 is not included because it's an open circle, and then it goes to the right forever. Because even though there's a circle here, it gets filled in, so it continues on. Similarly, the range is from 0, right? Because that's where this lowest point is, but 0 is included for the one on the right. So this is going to start with a bracket from 0 to infinity. So the lowest point is at 0, but it goes up forever, and 0 is included. And then this graph is increasing, starting at negative 2 with a parenthesis, because negative 2 is not included, to 0 with a bracket, because 0 is included. So on this piece on the far left side, then it decreases from 0 to negative 2. But notice negative 2 got filled in, to positive 2. Sorry. To positive 2. But notice positive 2 got filled in. So we can include that with a bracket. And then it increases from 2 to infinity. Okay, so that's the idea there. So why don't you all take a few minutes and try graphing these other ones. Pause the video and try graphing these other two with your ClassCalc app, and then we'll talk about them here in a moment. Okay, so now that you've had a moment to try these, let's go ahead and talk about them. So the first one is two horizontal lines. So from x is less than 2, I get the horizontal line at 3. So that would look like kind of like that, but drawn better. So that would look like this. And then we get the horizontal line at 1, but we include the point 2 for the other one. I also notice now that I screwed up the point here. So let me make this top one a little better. So at 2, we do not include 2. So I put a circle at 2 for this one on the top, and a graph like that. So then domain for this would be everything, because I've got an arrow to the left, arrow to the right, and we didn't skip over any x values in the middle. And the range is going to be pretty small, because the only y values we get are 1 and 3. On the piece on the left, we just get 3. The piece on the right, we only get 1. And then this graph is always constant, except for this little jump. So it's constant from negative infinity to 2 with a parenthesis, because that point's not included. And then it's also constant from 2 with a bracket to infinity along that piece. Okay, and then the last one here is two non-horizontal linear equations. So let's take a look at that. So we start at 1. For x greater than 1, that graph is going to start at 1, 2. So I put a circle at 1, 2, and then it goes on forever like this. and then the other piece ends at 1, so that would be at 1, -2, and it looks like this. So once again, we get a domain that's everything, because I don't miss any x values, but the range skips over these values here when it jumps. So it goes from -infinity to -2 with a bracket, because that one's included, and then it goes from +2 to infinity with a parenthesis, because that's got an open circle. And then this graph is always increasing, but it has a gap, so I have to write it as 2 separate arrows. So it increases from -infinity to 2 with a bracket, because that point's included, and then from 2 to infinity. So this graph is always increasing except for where we have the little jump. Okay. So that's the idea of how to graph piecewise functions. So now we also want to be able to write piecewise functions. So the easiest way to write piecewise functions like this is to use what we know about linear equations to write these. So like, let's look at the ones on the left together, and then I'll have you all try the ones on the right. So if we look at these two pieces here, we can see that they're both horizontal lines, right? So the way we write horizontal lines is by y equals whatever their y coordinate is. So this piece on top is y equals 2, and the piece on the bottom is y equals -1. And then we can see that the graph gets split at -1, right? So the graph's getting split here at x equals -1. So this, as a piecewise function, would be y equals 2 if x is, and then in this case, notice it's an open circle, so I want x to be bigger than -1, but I'm not going to include -1, so I'm not going to put or equal to, and I want it to be this piece, -1, if x is less than or equal to -1, because that one is included. Okay, so the same idea comes for these two. But to write the equation, we just need a slope and a y-intercept. So for this piece on the right, we can see that the slope is +1 because we go up 1 over 1, up 1 over 1. So that's going to be y equals x, and then we can add in the y-intercept. So the y-intercept here is at -1, so -1. And then for the one on the left, we can see that the slope is -1 because we go down 1 to the right one. So that'll be y equals the opposite of x. And then we can look for where its y-intercept would have been if it had continued on, which it would have been at 0, 0. So that would be +0, which we'll leave off for our final answer. So this is y equals x minus 1 if, so for this piece, we want x to be greater than or equal to -1, right? Here the split, once again, is at x equals -1, and the filled-in circle piece is on this graph. So that's why it gets an or equal to. And then the other graph is the opposite of x if x is less than -1. So we're going to the left of -1, so that's less than. And we don't include it because it's got an open circle. So then the last one here is the same idea. So here we've got a slope of 2 because we go up 2 over 1. So y equals 2x. And we've got a y-intercept of -2, so y equals 2x minus 2. And then this one has a slope of -1 because we go down 1 to the right one. So y equals the opposite of x. And it also has a y-intercept of -2. So this is going to be y equals 2x minus 2, or the opposite of x minus 2. And then if. Now in this case, we're going to get x is greater than 0 for the piece on the right, and x is less than 0 for the piece on the left. And it does not matter which one you put the or equal to on, because they both meet at the same point. So I'm just going to put it on the first one. So what I'd like you all to do is take a couple moments, just like we've been doing before, and try writing the equations for the 3 on the right. And then pause your video, and once you unpause it, we'll come back with the answers. Okay, so here we go with the answers for these. So y equals, in this case, we can see that we either get -2 for this piece on the bottom or 3 for the piece on the top. Okay, and so on the so if, and then we can see the break is at 1. So if For the piece on the bottom, we're going to the right, so if x is greater than 1. For the piece on the bottom, if x is less than 1. And then you just have to decide which one is 1 included with, and that's the one with the filled in circle. So that would be the one on top. So that would be the y equals 3 piece. Gets the or equal to. Okay, similar idea for the second one. So we've got y equals, and then you have to use the slope y-intercept. So the piece on the right here has a negative slope of 1, so the opposite of x. And then it would have had a y-intercept of 2, so the opposite of x plus 2. The one on the bottom has a positive 1 slope and a y-intercept of 2, so that's x plus 2. And then in the case for both of the split here is at 1, so the piece on the bottom is going to the right, so that's x is greater than 1. The piece on the top is going to the left, so that's x is less than 1. And then you have to decide which one is the filled in circle, and that's the piece on the left. So I'm going to do or equal to on the bottom function there. And then last but not least, y equals, the piece on the right has a slope of negative 1, so that's the opposite of x, and it would have had a y-intercept of 4. The piece on the bottom has a slope of 2, so that's 2x, and has a y-intercept of 1, so 2x plus 1. And then we have the split here is once again at 1, so the piece on the right is x is greater than 1, the piece on the left is x is less than 1. And in this case, just like on problem 73, you can put the or equal to on either one of them because they share that point. Okay, so that's everything for piecewise functions. The last function that we're going to talk about real quick is the greatest integer function. So this is the idea of a function where let me show it to you in the graphing calculator real quick so you can find that. So I'm going to clear out the graphs we've been using. And this function, I believe, is under algebra. Nope, I'm wrong. So let's see, where is it? It's actually under graph. And the one we're going to use is the one called floor. So if you notice on floor, the symbol looks like this. So there's basically two ways to write this function. By hand, you can write it like I've got it typed here, which is with two absolute value bars, or you can do a little half a bracket with the bottom piece of the bracket on it. And on your calculator, like we just saw, this is called the floor. And you can find it under graph. And so what this function means is it means what is the largest integer that is less than or equal to this number. So if I did the greatest integer function of an integer like 2, I would just get that integer 2, or like let me write those a little better. Or like negative 1, I would just get negative 1. So if I were drawing this graph by hand, for all the integers, I would just get themselves. Now, where things get interesting with these graphs is the stuff that happens between them. So like, for example, if I did the greatest integer function of 1/2, I want the largest integer that is less than 1/2. Well, that's just 0. And the easiest way, so that's just 0. So the largest integer less than 1/2, because 1/2 is right here on the graph, the largest integer less than that is 0. So for any integer between 0 and 1, I'm going to get 0. So I get a little line that looks like this. But when I get to 1, I put an open circle because I jump up to 1. If I pick any number between 1 and 2, like 3/2, that's 1.5. The greatest integer less than 1.5 would be 1. So for any value between 1 and 2, I get 1. For any value between 2 and 3, I get 2. For any value between 3 and 4, I get 3. For any value between 4 and 5, I get 4. So with positive numbers, you can really just think about it as throwing away the decimal. However, when you do this with negative numbers, it gets slightly trickier. So like this is negative 1/2, which would be negative 0.5. Well, the greatest integer less than or equal to that is negative 1. So we go to the left. So that's negative 1. So for any of the values between negative 1 and 0, you get negative 1. Between negative 2 and negative 1, you get negative 2. Between negative 3 and negative 2, you get negative 3. Negative 4 and negative 3, you get negative 4. And negative 5 and negative 4, you get negative 5. And if we use our graphing calculator to graph this, you'll see exactly the same thing. So if I plug in y equals the floor function of x, see how you get all these steps. Okay? So that's the idea. So this is what's called a step function. So the interesting thing about step functions when it comes to domain and range is that the domain is everything, but the range is only the integers. So it's just the integers. Because we skip over for the range all the decimals in between. Okay? So that's it for this section. I hope everything's going well with you while we're working on class online. Note that if you have any questions, feel free to call me or email me. I send around that information in an email to you all. And look out for